EDX Decision 1, Critical Path Analysis 1, Activity Networks. Constructing an activity network from a precedence table. So just as a quick introduction, every morning you want to toast 3 pieces of bread under the grill. The grill will take 2 pieces of bread at a time and will take 30 seconds to toast one side of bread. How long will it take to toast 3 pieces of bread? Amy says it will take 2 minutes. Bethan says it will take 1.5 minutes. Who is correct? If you'd like to pause the video and just have a think about the solution, you're welcome to. So if we call the bread ABC, how has Amy come up with 2 minutes? So Amy has put slices A, B together, and then she's turned them over to do the other side of A and B. Then she's put C under on its own, and then she's turned C over to do the other side of C. So that's 30 plus 30 plus 30 plus 30, 2 minutes. Whereas Bethan has been a bit more efficient, and her analysis of this has been to put A and B under together. Then she's turned A over and replaced B with C. So A is now finished. And then she's turned C over and then done the other side of B. 30 plus 30 plus 30, 1.5 minutes. So critical path analysis enables us to plan and monitor complex projects so that they are approached and carried out as efficiently as possible. Generally the question is, given certain conditions, what's the shortest possible time the project can be completed in? We will assume that tasks can be carried out simultaneously whenever the conditions allow this to happen. We need to be able to take into account that some activities cannot be started until others have been completed. And this topic has applications in manufacturing, constructing buildings and logistics and planning, etc. In general, a project is modelled using what's called a precedence table, and we draw what are called activity networks. First, we list the activities and their durations. We decide the logical sequence and identify which activities, depending on others, having been completed before they can be started. For example, the stages involved in recording and promoting a compact disc. So here is a precedence table for the recording and distributing a CD. So we can see, for example, taping the performance, designing the cover and booking the advert in the press have no precedence and can start straight away, side by side. They don't depend on anything else. Whereas D, taping the CD, tape to CD, can only occur after we've taped the performance A. E, producing the cover, can only start after B when we've designed the cover. And for example, at the end, putting the advert in the press can only happen after we've booked the advert in the press, dispatched the CDs to the shop, and I played the CD on the radio. You only put the immediate predecessors in the table. You don't, so it's just the ones that have to occur immediately before an activity can start. We're going to use what's called an activity on arc network for this process. This is done step by step and we work from left to right. So in this little example, you always have a starting node. So that's the start of the project. And working through the activities, activity A can start straight away. It has no preceding activity, so A can start straight away. Notice A starts at a node and finishes at another node. So it needs to have an arrow. We can only do A in one direction because we're working in time. So the edge has now become an arc. B has no precedence, so B could start straight away. And there's the arc representing B. C, however, can only begin after A has finished. So this is the event when A finishes here. So that's my second node, and that is when C can follow. D has to follow B. E also has to follow B. So I have a node, my third node at the end of B, and once B is finished, that's when I can start D, and I can start E. F follows C and D, so C and D both need to finish before I can start F, so I can bring those together at my fourth event, which is finishing CD, and that's the event when I can start F. G follows E and F, so G follows E and F, so I need to bring E and F together. So I bring E and F together, that's my fifth event when I finished E and F, and now I'm allowed to start G. And you always have one single finish node, which is the event when everything is complete. So now we're going to create an activity network for this scenario. So we start with the start node. And we look for the activities which have no precedence, and they would be A, B, C. So we can add A, B, C to the diagram. Now we look at D. D needs A to be finished before it can start. So D, we can add a node to the end of A and we can start D. We now look at E. We can do a similar thing there. E follows B, so we put our third node at the end of B, and E can follow B. Activities F and G both have D and E as precedence. So we can bring D and D together at a fourth node, so that's the event when D and D finish, and it's when we're allowed to start F and G. So now we can add nodes to the end of F and G, ready for the next step. So they're the fifth and sixth nodes. Activity H must follow F, so that can be added to the diagram. Activity I follows G, so that can be added to the diagram. Now J has to follow C, H and I. So we need to link H and I together at node 7, but we also need to bring in C. So C, H and I all finish at event 7, and J can now be added and the network is complete. So J follows C, H and I, and the 8th node is the event when the project has finished. We can now identify each activity. Each activity can be identified by a unique pair of nodes, I and J, and I should always be less than J. So for example, if you look at event, the first event and the second event, that is when A begins and ends. So A can be defined by 1, 2. B starts at event 1, finishes at event 3, so that can be B is 1, 3, etc. So J could be defined as J, it starts at 7 and finishes at 8. In the next session, we'll be using dummies in activity networks.